We did see the video last time, right? You remember now. So, given n atoms in a molecule, each one has 3 degrees of freedom if you are in 3-dimensional space, 3n degrees of freedom, and then the center of mass of the molecule will remove how many? 3 of the degrees of freedom, right, which is the, you can move the whole molecule from place A to place B. Center of mass is what, center of mass of the molecule is what is moving, and that is not going to change the vibrational degrees of freedom. So, 3 translational degrees of freedom associated with the center of mass of the molecule is not playing a role in vibrational motion. Other thing is to rotate the whole molecule. If it is linear, the rotation about the axis of that linear molecule will not do anything. So, only you will have 2 rotations if it is linear molecule. If it is non-linear molecule, you have 3 axes of rotation. So, you have to remove the rotational degrees of freedom also from the system. So, totally 3n minus 6, where n is the number of atoms in a molecule, that plays the role for vibrational degrees of freedom if it is non-linear molecule. Is that clear? Atoms, 3n degrees of freedom is total, and then 3 degrees of freedom is for translations, translational motion, 3 for rotational motion. So, 3n minus 6 is the vibrational degrees of freedom. Okay. If it is linear, molecules. So, I am looking at all these molecules in 3-dimensional space. Okay. So, linear molecule in 3 dimensions, again 3n to start with, this one will be again 3, this one will become 2 degrees of freedom, because one about its own axis it does not give you for a linear molecule like carbon monoxide, nothing happens. So, the number of degrees of freedom, vibrational degrees of freedom for a linear molecule will be 3n minus 5 degrees of freedom will be the vibrational degrees of freedom. Okay. Suppose I tell you that you are in a hypothetical situation that you are going to move only in the 2-dimensional plane, then what happens? Suppose I say that 2D space is where you can move around, okay? Then what all modifications will happen? 3n will become 2n and so on. Okay? Translational degrees of freedom will become 2 degrees of freedom. Let me look at nonlinear hypothetical molecule. Okay. How many rotational degrees of freedom? 1. So, totally vibrational degrees of freedom for a molecule with atoms on a plane, let us say, will be nonlinear molecule, what I am taking it. It is on a plane, but not lying along a line, it is on some equilateral triangle or on a square, but it is just confined to the xy plane or okay. And we have seen various things pictorially or in the video, the relative motions of the atoms without altering the center of mass of the molecule are the ones where we have to also rotation, does not alter the rotations. Those are the ones which is going to tell you exactly whether there is stretching, bending, which are called breathing modes, asymmetric stretching, symmetric stretching. You saw some of these pictures on the video. Can we understand this from your character table, projection operators, reducible representations, tensor product of representations? That is the theme of today's lecture. So, assumption is you have not forgotten character table, you know tensor product, you know how to get from the reducible representation the irreducible representations, and then we will see whether we could get the asymmetric stretching, symmetric stretching, all these things we would like to understand. Okay? Yeah. On the plane you will have about a point rotation, that is all. Huh. No, but you have to keep it on the plane, you are looking at it in 3 dimension. Just confine that I am on this floor, all the atoms are nothing beyond this floor, no going up or down.
But still ma'am, if I can on the plane, like if particle is fixed, like one can rotate like this, other can rotate like this. If this
no, those will be the relative motions.
Okay.
The whole molecule you can't rotate relatively different atoms in the molecule, that is what you are doing. You take the whole molecule, rotate the whole molecule, the system is intact. Take the molecule, translate the whole molecule, the system is intact. So, those two are the 3 degrees of freedom. Those two are the 3 degrees of freedom which you have to worry about for translation, which is like center of mass of the molecule. Similarly, you have a rotational. Not able to see whether this works. Okay, is that clear? Not the relative rotation. All those relative motions are like displacements about its mean position, which will give you the vibrational degrees of freedom. It will not give you the total rotation of the molecule. If you have seen the video, it is just at the axis on which the whole molecule is rotating, not relative atoms in the molecule. Is that all right? Okay, fine. So, now I am going to try and do a little bit of warm up on classical mechanics to tell you how difficult or how cumbersome it is to solve equations, and then I will lead you to group theory to show how simpler it is. It can work for many complex polyatomic molecules. Okay. This is the theme on which I am going to pitch today's lecture. Okay. Okay, so this is a warm up which we did last time also for a complex system. Anyway, I have said this, there are a number of degrees of freedom, and that degrees of freedom will depend on your number of atoms and all these things I have explained on board. So, given that there are s degrees of freedom, so you just take them x1 till xs are deviations from the mean positions of the atom. So, it gives you displacements of the atom about its mean position in a molecule. So, those are what we call it as excursions of mass points, and typically you will have a Lagrangian which is dependent on x1, x2, xs, which I put it as a column vector and row vector. In between there will be a matrix. so that this whole thing will be some kind of a number, or is that right? So, you have a matrix, a column vector multiplying the matrix here, x dot is the time derivative of these s degrees of freedom, and x dot transpose is the column vector, and then row vector, this is a column vector and this is a S cross S matrix. Okay. And similarly, you will have a kinetic potential energy term where it is only on the positions. So, displacements of the mean positions, which I call it as excursion. This is the formal Lagrangian which you can write. It will be coupled set of, if you try to find the equations of motion for this, there will be a coupled set of second order equations to solve, right. You might have done this. The only way you can make it into uncoupled equations like this is by doing a suitable diagonalization matrix and then find the basis eta for those diagonal eigenvalues. Diagonal eigenvalues are the frequencies. I am sure you would have done this. If you have not done it, just take a 2D or a 3D system which is coupled, try to diagonalize the matrix, find the eigenvalues, then try to use the matrix which allows you to diagonalize such a matrix, and that will define for you the position excursions over the etas. Etas are what we call it as a normal modes. Okay. Is that clear? Okay. So, with this in mind, let us look at an example, nonlinear molecule. Okay. So, I said overall translation molecule is eliminated by imposing that the center of mass of the molecule does not get displaced. So, you put that to be 0 origin. So, you have, remember an example like a water molecule, right, the 2 hydrogen atoms and this is the oxygen atom, and we have this equation for center of mass of the molecule does not get displaced. Okay. So, you can determine what is, I have given the bond length in the undisplaced situation as L, and the angle made with respect to the oxygen molecule I am calling angle subtended by the 2 hydrogen on the oxygen molecule is 2 alpha. Okay. Clear? So, location of the center of mass of this molecule can be written down. Okay. You can find that the x is 0 and y will have this, sorry, z. I am taking this to be in the x and z coordinates. Okay. Okay. So, now rotation, this will clarify your question. Rotation of the molecule can be eliminated by putting angular momentum about center of mass of molecule to be 0, and if you try to use these 2 equations, you can simplify and write this constraint which has to be satisfied. So, basically what do we see? You have 6 degrees of freedom, okay. You have 1, 2 and 3 constraints, clear. So, essentially how many degrees of freedom you have with you, which will be the vibrational degrees of freedom, is 3 degrees of freedom. Okay. So, translation and 1 rotation puts 3 constraints on the 6 degrees of freedom. What are the 6 degrees of freedom? You have x2 z2, capital X capital Z, x1 z1. If I am looking at it in this, the y coordinate is remaining the same. If you take this, then you find that there are essentially 3 degrees of vibrations possible, and we are interested in looking at the 3 degrees of vibrations. Okay. So, I am also trying to show you how systematically you can solve these situations in classical mechanics, okay, so that you appreciate when I do the group theory that this is doable from group theory. Okay. So, for nonlinear triatomic molecules, so we have to have, which preserves are the vibrational modes subjected to these 3 constraints. So, the only motion where you are allowed the freedom of displacement or excursions of these atoms in the molecules are either the bond length, this length could change, this length could independently change, okay, and you can also have the angle 2 alpha could also change because of the relative displacements of the atoms in the molecule, clear. So, these are the only possibilities which I can pictorially see here, which may not be visible when we go to complex polyatomic molecule, but let us understand in the simplest case and map it to group theory, so that you can believe in group theory for complex polyatomic molecule. Okay. So, bond length changes, this is one possibility which will be 1 vibrational degrees of freedom, and then you can also have the bond angle changing. Okay. These are the 2 possible deformations of the molecule without altering the center of mass of the molecule and rotational degree of freedom. Okay. Okay. So, how does bond length change? You can make this length to change, for example, here which I call it as delta L1 is the change in length of the bond length between capital M and small m for this case, and delta L2 is the change in bond length for the mass with coordinates x2, z2 and the capital M with x and z. Okay. And you can also have a rotational constraint. Okay. So, in fact, this is given explicitly in Landau-Lifshitz mechanics book, in case somebody is, I am only giving the final equations here. If anybody is interested to derive these things, you should go back and look at Landau-Lifshitz mechanics. Okay. So, the rotational deformation delta 2 alpha, this is given by these changes in which involves x, x, z, okay, all the 6 degrees of freedom and the angle alpha. Okay. So, so far so good. Looking at these constraint of center of mass, angular momentum being about the center of mass being 0, you can try to rewrite the Lagrangian. This looks ad hoc at present, but let us just make a change of variable to a new variable q1, which is the sum of x1 plus x2, q2 is the difference between x1 and x2, q3 is the sum of z1 plus z2, and you will also see that the center of mass of the molecule and the angular momentum about the center of mass being 0 will put in some kind of a condition here between q1 and z1 minus z2. So, I am basically trying to say that if you had 2 coordinates, you could sum up the 2 coordinates and take the difference. They are 2 linearly independent objects, but when it comes here to z1, the other one is actually related to q1 and the angle alpha. So, it is not going to be a new degree of freedom. Okay. z1 minus z2 should not be a new degree of freedom, it is going to be constrained. So, q1, q2, q3 are essentially the 3 degrees of freedom which can capture the vibrations of this nonlinear molecule made of 3 atoms. Okay. To find the normal modes or actual vibrational degrees of freedom, it could be a linear combination of 1, 2 and 3, that I am not really looked at it right now. I just made a change of variable and then I can write for this system the Lagrangian. Okay. So, the Lagrangian will have a potential energy, there will be potential energy due to vibrations which involves delta L1 squared, another vibration with delta L2 squared, and there could also be a vibrational mode due to delta of the angle change. Okay. So, you will have those terms added into it. So, this is what I am saying, you will have a spring constant, it is all simple harmonic, let us take it to be small displacements, let us not do a violent vibrational modes are like small displacements about its mean positions. So, they will all be simple harmonic, okay. And let us take the spring constant due to change in bond lengths to be kappa subscript L, and another spring constant due to change in bond angle as another kappa alpha, and in terms of Q you can write the Lagrangian for the system. Okay. So, try and redo this, rewriting it for the system of 3 masses, you have 2 masses and a capital N. So, try to write it out explicitly, okay, and you will find that you have equations where you have a Lagrangian with q1 dot squared, you have a Lagrangian with q1 squared sin squared alpha, and kappa L is the spring constant for the change in bond length, okay. And similarly for q2 also you will have a piece which depends on kappa L, but you will also have a kappa alpha and so on. So, you have this. What do you do next? Given a Lagrangian, you try to find the equations of motion for q1, q2 and q3. This is what you will do, right. Everybody is bored, looks like everybody knows. So, good, if you know it, it is good, if you do not know, do not worry, but this is the cumbersome process in which a mechanics student, classical mechanics student works out the normal modes in, and I am sure they would have got problems in exams and for linear molecule finding the normal modes, yes or no? Yes, okay. So, equations of motion for that Lagrangian. Interestingly, you see that this first equation is completely decoupled. It has no coupling to q2 or q3. So, straight away from here you can read off that q1, which was defined to be x1 plus x2, should be one vibrational mode with this frequency. Okay. And again this equation has a coupling between q2 and q3, and this one has between q3 and q2. So, they are coupled set of differential equation, and you know how to solve it. What do? You write the determinant, you try to find a normal modes by diagonalizing such a matrix, right. So, I will leave it to you to check this. I will put this slide. I want you to check because it will help you to understand the group theory way of doing it. Okay. Right now it is still mechanics, whatever I have said. So, you see the steps I have gone through. I have gone through systematically, but it is a little tedious. You need to literally do these things to figure out that q1 is a normal mode with coordinate x1 plus x2, but what we will see is from group theory we can actually get x1 plus x2, and then because we have done this hard work you can appreciate x1 plus x2 is a normal mode I get from group theory. Okay. Is that clear? So, some of the steps of math I am not going through right now here because it is not a mechanics course, but anybody is interested you can come and bother me if you are not getting in between steps, but you can look at Landau-Lifshitz and you will be able to get these steps. Okay. So, I am not doing the diagonalization of this coupled set of two equations to determine what are the normal modes, which will be a linear combination of q2 and q3 and an orthogonal linear combination involving another mode. Okay. So, this I am not doing it now, and when you diagonalize it you will find two eigenvalues. If the two eigenvalues are different, then only you call it non-degenerate, right. Do you expect it to be different or do you expect it to be same for this molecule which we are looking at? C2V is the symmetry. The character table tells you that you should have only 1D reps. So, you better get all these eigenvalues to be different. Okay. It has to be different, it cannot be degenerate. Okay. Check it out. I am sure you can take this and diagonalize it and find the frequencies. Okay. So, 3 vibrational degrees of freedom will involve Q1, Q2, Q3. Turns out that Q1 itself is a vibrational mode, which is one frequency. What is the frequency? Frequency is going to involve this factor times this one is omega squared. Okay. So, this is non-degenerate one normal mode or one vibrational mode, which is straight away Q1. Q1 is not talking to Q2 and Q3. Linear combination of Q2 and Q3, what linear combination? You have to diagonalize this and find out and what are the frequencies. Okay. I am trying to tell you that you will find each one to have a distinct frequency, you cannot have the same frequency. If you are doing other molecules like methane, which was shown in the video, you will start seeing, if you do this rigorous exercise, there will be some frequencies which will occur 3 times because there is a 3D rep in the character table. Okay. Or if you had a C3V symmetry, you will get 2 times, which is associated with the frequency should repeat twice, and you should be able to find 2 distinct normal modes sharing the same frequency. That is why they start doing that mixing and joining together, you know, you remember. And you can see that in the methane molecule, there are 3 degenerate vibrational modes and they combine together and so on. When will you get degenerate? Comes from the symmetry of the molecule. Okay. I hope you are appreciating what I am trying to drive in, how simple looking, how complex looking, where group theory can play a very important role. Yeah. You can treat it to be a 2 dimension, or you can also treat it to be a 3 dimension, but then you have to remove the translation along the y direction and the rotations which is involving the other. Yeah, I will come to it. C2V in the sense that this is an example of a water molecule, and I know that the 2, I put it as 2 identical M's. If you do a C2 about the Z axis, you do see that this hydrogen goes into the other hydrogen and vice versa. It will be still, if you treat the Z axis to be the C2 axis, it is still true, no? And sigma V to be like the XZ plane, it is still true. Okay. Is that clear? So, I am just looking at it from purely from the action of the group theory also, and you can treat it like a 3D problem, but then you have to remove those. I have to put the center of mass coordinate for the y also. So, basically I could have given x1, y1, z1 and complicated the situation. Instead I thought anyway y is not playing a role with all these symmetries of this molecule. I can look at it as a C2 axis on the Z axis, which takes the 2 hydrogen atoms to each other. So, I thought it is better to confine to a simpler 2D situation, but you can extrapolate it to 3D.